All right, three, two, one. All right, hello everybody. We are back, podcast number 3 for physics. Today we're going to be covering time itself and the weirdness of time. This was brought about by the recent movie by Christopher Nolan, which we'll get to in a moment, but it's called Tenet. It's a fun time. You saw it in theaters, right, Lee?
Oh yeah,
How was
I love Chris Nolan.
how was the experience? That was your first movie, I assume, since
First movie
Corona?
back post
Yeah.
COVID. Yeah, it was nice. It was socially distanced at Alamo Draft House, and yeah, it was just great to be out. And Christopher Nolan movies are always best experienced in theater, big screen format.
Yeah, I agree. I went with my friend, and we were the only ones in the theater, so that was kind of cool because it was still like opening week, I think. So that probably
Yeah.
won't happen again. But yeah, so first off, a couple things here. We wanted to, in terms of an introduction or in terms of describing why we're even doing this podcast, I think it's helpful to stop every once in a while and just sort of think, okay, so why do we even care about physics? What is it about discussing these topics that makes us so interested, and we assume makes one or two other people interested too. So let's pause a moment. Let's zoom out to the macro level and think, okay, so what is it about physics here? You've been studying physics for a very long time, Lee, and yet you still want to explore these topics more. I mean, even in our pre-podcast meeting here, you were fascinated by these topics, and they seem to be almost eternally interesting, I guess, each time you think about them. So what is it about physics that you enjoy?
Uh, yeah, I guess my initial interest in physics was always that it reminds me a lot of puzzles and games. Solving, at least, solving physics problems is akin to, getting to the end of a puzzle, right? You get that satisfaction when you finally solve the puzzle. And so that was my initial fascination, is that in solving rudimentary physics problems, it is just like solving a puzzle. But then that passion sort of grew, and I got more enjoyment out of just the discovery process. Even if there wasn't an answer at the end, which many physics questions and paradoxes don't have a solution. It's it's that thought experiment of going through and thinking about it that is just so fascinating. And it is the fact that there is still so much in the world, in the universe, that we just have no idea about. And that is just fascinating to me.
Yeah, when you were mentioning a puzzle there at the beginning, that reminded me of James, who works with us. People listen to this podcast. Some of you will know James, but one time he's a big puzzle guy. One time he was working on this like massive puzzle, and it took him forever, but he was just, dedicated to it. And he got to the very end, and there was one puzzle piece missing. He was so angry. And I can only imagine that's how it is for a lot of physicists. I don't know if they're angry or not, but they get to the very end, and there's always something missing, right? There's always some new thing that they're going to have to account for and then redo the whole puzzle eventually.
It can be maddening. Imagine spending your entire life's work on solving a physics conundrum, only to find out that there is no solution for it, or that it would work. And many physicists have gone crazy with that exact thing. Yes,
I would assume so. It makes sense. But yeah.
So Josh, what is your fascination with physics?
Good question, Lee. I guess certainly not on the technical level. I remember I really only took one physics class, and that was in high school. And I was somewhat interested in it, but I think at the time, just the amount of formulas that I had to memorize and then math that I had to work through kind of put me off of it. I think the concepts behind physics, though, have always been deeply interesting to me, to understand why the world is as it is, or at least to get another perspective of why the world is as it is, I think is something that's going to always be curious to me, and I think curious to most people. And physics is one of the most technical processes that we've developed as a species up to this point. And a lot of it's very complicated, but it's still dealing with things that everyone has thought about or wondered about at one point or another. And I think that's one of the reasons this podcast could be helpful, or at least why I find it interesting, is because I have a self-proclaimed expert like yourself. No, I'm just kidding. You don't like that term.
No.
But Savant? I don't know. What should we call you?
Oh, no,
Lover?
neither of those. I am maybe an intermediate physicist, a passionate intermediate physicist, maybe is
A PIP,
a
passionate
PIP.
intermediate physicist. Okay, PIP. But I at least am able to discuss these issues and ask good, I think, decent questions to you, and then you can help maybe give me some more context and flush out some of these questions for me. So that's why I enjoy it.
Yeah, great.
Well, in that regard, let's get into some of these questions here. So today we're covering, like I mentioned at the beginning. Oh wait, I always forget to do this. Okay, if you're listening right now, please subscribe to our channel, to Lee's YouTube channel, to my podcast. Again, share it with others if you enjoy it, or if you find it half interesting, or you think someone else would enjoy it. Yeah, the more people that listen, the more interesting questions we can get in our next YouTube live session.
Yeah, and on YouTube, you can't just click the like or subscribe button. You have to smash it. That's all the popular YouTube say, oh, smash it. So I don't know what that means to smash a button. Maybe you can never use it again, but you're supposed to smash the like or subscribe button.
Yeah, I'm a little too old to truly understand what that means, but there might be like an epidemic of broken computers across the country if
Yeah.
people take it too seriously. Okay, so back to the issue at hand, time. Time's already progressed. I don't know how many minutes, about 10 minutes now since we started this podcast. And it's obviously not going to go backwards, or will it go backwards? Like we mentioned, this was brought on by Christopher Nolan's new movie, which is, I would say, mind-bending is a good way to describe it. Lee, would you like to maybe give, not the plot per se, but what are some of the most interesting sort of physics concepts that Nolan like plays around with in this movie?
Yeah, just like his previous movies, he sort of questions the nature of how we observe the universe. One of my favorite movies is Inception. That one has to do with dreams and being able to recreate and even get inserted into someone else's dreams. Tenet covers the concept of time and basically the directionality of time. Is it possible to create a device or a substance which would allow you to travel backwards in time? And if you have a forward stream and a backward stream of time happening at the same time, is there any sort of paradox? And what could you manipulate if you did? So it is very interesting. And so I think that's what it is like multiple directions of time.
Yeah, there's a whole lot of what if questions we could ask about that movie. Perhaps some of them are plot holes, perhaps some of them are quite brilliant, but we'll leave that perhaps for another full podcast, maybe after people have had a chance to see it.
Yeah.
But that does lead us into a good overview of what we're going to discuss today. You've already touched upon most of them. We're going to start off here talking about the direction of time itself. Again, why does time always move forward, or does time always move forward? And then from there, we'll move on to measuring time. Again, how do we measure time? Why do we measure time? How finely tuned is time? Can we get it down to the most micro level? And then finally, everybody's favorite, paradoxes. I love these ones just because they make no sense and they hurt your brain, which I enjoy. So we'll get to those last. Again, for some reason, when you start traveling back in time, there's a lot of weird things start happening. A lot of paradoxes start immediately emerging.
Who would have thought?
I know, who would have thought? I'd say certainly, I mean, I don't know what other kind of concepts there are like that, but it does seem like time travel seems to produce the most paradoxes right away. Like as soon as we start questioning something that we've always sort of assumed that time just goes forward, and we're like, well, what if we went backwards? Everything just falls apart. So, all right, let's start off here with direction of time. So there's a couple ways to think about this. One, if we take it from the personal level, obviously time always moves forward, right? As much as we don't want it to, as much as we want to stay the same age, we want to maintain our youth, or perhaps as much as we want to go forward quickly so we can get to something that we were waiting for, it will progress at the same speed. But it also progresses quite relatively too. Like Einstein's famous quote about this was, I think, like a minute sitting on a hot stove top feels like an eternity, or it feels like an hour, where an hour spent with a beautiful woman feels like a minute, something like that. There's
Yeah.
many different ways you could phrase that, but um, so time itself is relative in many ways. If you're doing something you love versus something you hate, time will go more quickly or less quickly. But it does always seem to move forward. Is that indeed true on the technical level, Lee?
Yeah. And maybe just a quick comment on the perception of time and time's relativity. I feel like that might be just as much a biological and neurological question as it is a physics question. Like how we perceive and save memories probably disrupts our perception of the passage of time. So we will not cover that today because I am definitely not I'm even less of an expert in that than I am in the technical nature of time. So yeah, really interestingly, when you start studying physics at a higher level, you start to see that a lot of microscopic physics properties are time invariant. And that means that time is essentially symmetric. What happens, it happens in the past and happens in the future, happens so at the same rate and are symmetric. So therefore, you could move an equation backwards in time and you can move it in forward in time, and it's essentially just there's no difference. That is certainly a great theoretical treatise, but it doesn't make sense to us on the macroscopic level, right? Like as you said, we only observe time in one direction. And so sort of a classic example is like if you were to watch a video of an egg cracking, you would know that that's in forward in time. But if you watch a video of an egg uncracking, going from a cracked state to a whole, something is wrong. The universe doesn't work like that. So macroscopic observations are only one directional. And I think probably the reason why um, there's so many paradoxes is because causation determines so much of what we do in the world, right? Time, I think, is even more of an important concept in space, right? If you think about when you go to meet somebody, it's just like, what time are we meeting, right? Like where we're meeting, we'll figure that out later. But like we have to be there at the same time. We have to make sure we're going there at the same time. And if you meet somebody, then you'll meet somebody after. And if you eat, then you won't be hungry after. So there's a lot of causation that happens with time. So certainly we observe it to be that way. Is there any physics that dictates that it should? What do you think, Josh? Is there any physics that says that it has to go one direction?
I would assume that there is at least some physics out there that says it has to go one direction, because it wouldn't make sense if it didn't actually exist. If that makes sense. Like, I'm sure they're going to be, and we'll get into it in a moment, but I'm sure they're going to be interesting theories that arise when we view things on like a microscopic level. But I think our perception of time on a macro level is so, like, it's one of the most fundamental sort of assumptions we live by. I mean, just think of it psychologically. If you were to say, like, anytime someone's stuck in the past, that's not a good thing, right? Or if you're trying to return back to something that happened to you previously, that's never going to result in growth or maturity on a personal level. Well, maybe not never, but those sorts of things, you can't always be looking backwards or even try and return to the past, because it's just not helpful. Now, you can look back on the past and try and, resolve past traumas you had, but you can't go back there. So I don't know. What do you think about that?
I think you've hit on something very important, which probably falls outside of the realm of physics and falls under more of the field of psychology and potentially sociology. And I think that's that I think as a species, what makes humans unique is we can regret things, right? We can focus on like what we did in the past, and we can use that to change our behavior. I think we probably do that to our detriment. I can't tell you how many hours or days or months I've wasted thinking like, I should have done this instead of this. Well, yeah, sure. But there's nothing you can do about that now. So you stressing is not doing anything. Think about, if it happens again, what would you do differently, or how would you position yourself? And The physics driving this has to do with thermodynamics. Doesn't seem like that would be a field that would dictate our passage of time, but the second law of thermodynamics states that the entropy of the universe is always increasing. It's actually a little bit more technical than that, but that's essentially what it says. And so you say, oh, okay, great. The entropy always increases. What is entropy? Entropy is essentially a measure of the disorder in the universe or the disorder in a system. So an egg in its natural state right after it's been laid, it has relatively low entropy as compared to an egg that is cracked. It's very disordered, it's asymmetric, it's very difficult to quantify it. Same thing like if you have an ice cube, a perfectly cubic ice cube, you could define it really well. Well, if you take a jackhammer to that and you smash it into thousands of pieces, it's a lot harder to describe that state. It's a lot more disordered. And so it now kind of makes sense that time has to flow forward because things are always getting more disordered, right? When you are a baby, you present some disorder in the universe, but as you grow up and get older, you have more and more things, you have more information, you persuade other people's information. And even as the universe expands, it's harder and harder to describe the universe. And so, that's basically what drives the causation or the one directional movement of time is that if entropy is only going to increase, then time can only go forward. You can't go backward again because it would it would be very weird for us to just like we had eaten something and now we have uneaten it and now the egg is uncracked and now it is unlaid and that chicken is unborn. It doesn't make sense to us. So
Yeah. Although, I mean, the interesting thing there is it seems like while the law of the universe is that things will tend towards disorder, I would think that the anomalous thing about life itself is that life is the struggle for order. Because like if you're a baby, you're not going to feel disorder until you're probably, I don't know what age these days, maybe 50, who knows? Maybe you could tell me a little bit better than me. No, I'm just kidding.
Hopefully you don't wait till that long till you realize your life is disordered.
Well, but you can feel things change, right? You can feel the same sort of like you feel different. And then as you end like near the end of your life, obviously once you die, that's disorder, right? You like dissolve out of, I mean, whatever happens next, it's disorder. But there are brief periods of order, like even the egg or example that you gave, the egg itself has to be formed within the hen, right? And that is a creation of order for some reason. And then you crack it and you can't get it back after that. Like once you crack it, there's no going back, which is the part that makes sense there. But it is this strange thing about life that there's some weird clawing towards order for some reason.
Yeah, well, I think again, I think that's definitely a psychological construct that we like in our mind, even like the difference between your room being organized and your room being disorganized likely doesn't change the entropy that much. The entropy, it's tough to visualize, but you could probably just think about it as how easy is it to describe the state of it, right? So you could pretty easily describe the state of a newborn and say, here's from the time he was born, here's the sonograms, here's the weight at birth, here's the eye color, here's this. Imagine trying to describe your entire life to somebody, right? Like to describe every single person that you influenced, everything you bought, everything you created, that is all adding other variables into the universe. And at some point, it probably becomes increasingly difficult to quantify all of those. So
yeah, that makes sense.
Yeah. So yeah, I think probably a good follow-up to that is to think about the reason why we are, or one of the theories of why we're in an increasing entropy state is that the Big Bang started at a minimum entropy state. So at the point of the Big Bang, it was pretty easy to characterize the universe. And after that, you know, particles started, or atoms started getting bigger and bigger. It started off by quarks getting together and making hydrogen, and then they made helium, and then other sort of systems started to come together. Then planets started to form, and then biological beings started to form. And so that low entropy state, essentially the only way to progress from there was to be in an increasing entropy state. So
Okay, so very similar actually to a newborn, I guess, in terms of analogy. At the beginning, pretty easy to describe. As it expanded out, more and more things happened, more and more complexity occurred, which led to more disorder and entropy.
yep.
Interesting. So that means that time can only go forwards. Is there a way that time, I mean, how would we even conceive of time going backwards, though? I mean, would we have to reverse entropy, basically?
Yeah, I think you could consider, if you considered the universe starting in a maximum entropy state, it's kind of tough. To me, it seems kind of tough to visualize that like, imagine the universe starting with everybody already in it, right? You just came to being, and all of a sudden you're just in this maximum entropy state, and then all of a sudden you start getting younger until the point at which you die, which is what we consider now you being born. But it would essentially just, the life cycle would just be reversed. You start really old, or you start older, and then you always get younger, and then you just observe that, essentially what is interesting is, as we know it, the physics seem odd, right? So gravity would go up instead of down.
How would that
Right?
work?
Well, think about how we observe things, right?
Oh,
So if I
okay.
hold this
Yeah.
pen,
Yeah.
in one
Interesting.
second, it's going to be here, and so I know that if I start a stopwatch, and I drop something, it's always going to go down.
Hmm.
If time is going in reverse, I know that if I let go of this out of its hand, it's going to go up. And it's kind of tough to think about it, but I guess that is one possible way to think about time going in reverse.
Okay, so that would basically this just then kind of be the end of this universe, and then work your way backwards in a way.
Yeah.
So then time, that seems to be, I mean, this is kind of another topic perhaps, but time and space, are inextricably linked, because both of them create entropy. So if you're going forward in time, more entropy occurs. If you go backwards in time, less entropy occurs.
Yes. Yeah, absolutely. And I think you just hit the nail on the head, Josh, that like, that's why space-time is considered, one object. Is not, this is space and this is time. They are linked through gravity.
Okay. All right. That is fascinating. Next up here, we have measuring time. So again, since time really only goes forward, at least on the macro level, there are obviously different ways to measure time. What are some ways that physicists use time, or measure time? Because I mean, obviously you can measure time by the sun, by the passage of days. But again, even days themselves are different for where you live in the world, or what season you're in. That all changes, but there are ways to more objectively measure time. Is that correct?
Yes, absolutely. And we already discussed in one of our previous podcasts that time dilates depending on whether or not you're close to very massive objects like black holes.
Mm-hmm.
But assuming that we are just sitting here on Earth, the atomic clock is probably the most understood time measuring device. You can go on Amazon now and buy a clock that is synchronized to an atomic clock for $10 now. And it gets a radio signal from the atomic clock so that you are always on the same time as everybody in the world. For the most part, it seems like overkill to have to even have something that is accurate to within a second, right? Like if I show up a second late for our lunch meeting, is that really, like, would you even notice that, right? Like would you be looking and saying, you said you were going to be here at 11:30, you're at 11:30 in 1 second, right? So the atomic clock measures events to within femtoseconds, which is a billionth of a millionth of a second.
Okay, that's pretty easy to comprehend.
It's pretty easy to comprehend, right? It's just like, boy,
Yeah.
if I only had a few extra femtoseconds in my life, think about how much more I could get accomplished.
Yeah. I mean, how do they even, this might be too technical of a question, but how do they even do that? How do they like measure to such a fine degree? What are some ways that they do it?
God, I probably should have done research on this. Yeah, I think it has to do, I could be mistaken. I think it has to do with a cesium atom. So they take, they'll take an atom, and if you look at the periodic table, there's these things called isotopes, which is just an atom which has more neutrons. And for the most part, atoms traditionally only like to stay in one state, right? They know that's like, hey, there's too many neutrons in here. Like, we'll keep it here for, a minute or a day. And so these things have half-lives before it will decay. And so there are certain atoms that have very exact decay rates. And so they find something that has an exact decay rate, and they're able to measure it on that time scale. And they know, hey, this thing always happens at 6 femtoseconds. And I think that is the accuracy, plus or minus 1 femtosecond. So I think that's what the atomic clock, and that's why they call it an atomic clock. It's an atom with some sort of decay rate. Again, I could be mistaken on whether or not it's cesium, but it is based on that type of structure.
But what observes it? Because obviously the humanists could never could never say, oh yeah, that was 6. That was definitely 6, not 5 femtoseconds. Like, how do they even observe it?
Yeah, that's a really good question. And there's an entire field of physics dedicated to measuring short times. But yeah, they use a variety of different techniques. You're right that humans, for the most part, we operate in millisecond timescales. So like, I think the fastest human reaction time is like 40 milliseconds. So that's 40 thousandths of a second. This thing is happening, on a millionth of a billionth of a second. Like you just couldn't hit a stopwatch fast enough. And even a stopwatch, the electronics inside of it aren't that fast. And so they use these devices. It's probably something like a streak camera. A streak camera, essentially, when a particle gets emitted, let's say from cesium, if it's probably an electron or probably a photon, they will have a device which will streak that photon across a screen. So you can imagine that, like, when it comes, you basically like apply a really fast, it's an electric field to it. And so you can find out exactly when that thing came into the streak. So anyway, it's a fast type of, they call it a camera. It's not a camera as you and I know it, but they use it to measure very fast particles.
Interesting.
Yeah.
So femtoseconds, that's a billionth of a millionth of a second?
Mm-hmm.
Okay. And then I assume, as humans always do, we want to get finer and finer. We don't want to stop there, right? So are there greater, or I guess even smaller times than that we've been able to observe? Not we, but you know what I'm saying.
We, the royal we, the
humanity.
Yes. I spent a lot of time in working in ultra fast laser physics, and so we can actually create laser pulses that are 1,000 times faster than the atomic clock in what's called the attosecond time scale. And physicists often get accused, mostly by engineers, of just doing things for the sake of doing them without any practical application. This actually does have practical applications. When atoms decay or when plasmas interact, when you're trying to create a fusion reaction, electrons and photons move on time scales very fast, femtoseconds. Atoms rearrange themselves on the scale of attoseconds. And so if you want to find out exactly what's happening to a system as you apply a laser, as you apply a magnetic field, these are two common fusion devices. They do magnetic fusion and laser fusion is the two that I sort of worked on. You want to know what happens to this system as I start this reaction, because fusion reactions are based on symmetry. And so if you create a very fast laser pulse, what you can do is you can make a system, you can make an atom stand still. So imagine that you have a nucleus and you have a number of electrons around it. If you can hit it with a laser pulse very fast so that you immediately excite an electron out of that state, you can recreate what the system looked like at that point, but it's dependent on how fast you can get the electron out of there. You can get the particle out of there. So they do all of these tricks with laser pulses where you just can make them shorter and shorter. And it has to do with passing them through crystals. You can imagine that, like, if you have a laser pulse that is 1 second long and you have another pulse that is 1 second long, what you can do is you can put them in this doubling crystal, which is what we talked about in our last podcast. And if you delay it just so that they only combine at a certain time, then those 2 1-second pulses can create a millisecond pulse. Well, then you can put 2 millisecond pulses to create a microsecond, and then so on and so forth. So that's how you create them, and that's the application of them.
Okay, fascinating. I assume there's some sort of limit to that. Obviously, I guess you just get to 0. Is that the limit? Like, how do you keep going shorter and shorter and shorter?
Yes. So, I think in our current means of making short pulses with lasers, there's probably some limit. I don't know what that limit is. There is certainly maybe this is your question, is how short is it possible for you to even go in the universe?
Sure.
A lot of this is dictated by something you really like, which is the uncertainty principle. And that states that traditionally you can't measure the momentum and the position of an object with exact precision. You can measure exactly where a particle is, but you're not going to know exactly how fast it was going. Or you can measure exactly how fast it was going, but you don't know exactly where it is. You can change the physics of that equation, and you can relate it to energy and time. So at some point, if it's energy times time, can never be below a certain limit, then it's probably just also a measure of how low of an energy state can you get, and that will dictate the shortest time. It's currently unknown. It seems logical, and most physicists probably would argue that there's got to be a lower limit. We just don't know how finely you can tune that.
Okay. Yeah, again, it's hard to even kind of comprehend what that looks like at that sort of micro level in terms of time.
Femto level even.
Yeah, femto, even whatever's above femto.
Femto, atto. Actually, yocto, I think is...
Yocto, I like that one.
Yocto, yeah. 10, that's a millionth of a millionth of a millionth of a millionth of a second.
Is that 5? 5 millionths? Exponential?
4.
4?
4,
Okay.
that's 4 millionths. So 10 to the minus 24. So, it's kind of like, it's just like astronomical figures when you talk about, how big is this universe? And you think about the number of particles. It's way past what humans can understand. $1 billion and $1 trillion is even tough for us to comprehend. So this is just going the other way. It's like you start dividing things so finely that you don't have any basis in reality for what something that small looks like.
Yeah, that reminds me of Zeno's paradox. Have you heard that before?
Hmm.
Um, which I think, like you said, so the paradox is, let's just say you have a turtle in a room and the turtle is going towards the door. If you said, okay, so this turtle is going to go halfway towards the door and it's going to stop, and it's going to go halfway towards the door again and then stop, and it's going to keep doing that, it never actually reaches the door, theoretically. And that's, again, this leads excellently into paradoxes themselves with time, because there is some kind of, there's some breakdown. Something happens on the micro level at some point where you just kind of have to leap over the threshold into reality from theory, if that makes sense. I guess that's kind
Yeah.
of what humans are. We're kind of the go-between theory and reality. Um, but yeah, the Zeno's paradox was always so like, it's so brilliantly simple and ridiculous, like almost ridiculous. You're like, well, of course the turtle is going to pass the doorway, right? It's just going to keep walking. But if you did it with by mathematical principles, it actually, I mean, I don't know math that well, but it never does get to the
No,
door.
they would say that's a calculus or maybe even a pre-calc
Mm-hmm.
concept that's called the limit. The
Mm-hmm.
limit,
Mm-hmm.
as time approaches infinity, the turtle reaches the door, but in reality, it doesn't ever actually get there. It might get 99.99999% of the way there in our lifetime, but it doesn't technically make it there.
Right, right. Which again on the surface sounds ridiculous because you just like, well, it does get there, it just walks across. But you're right, like when you break it down to theory, there's some things start to some things start to break down a bit. So this leads into, I mean, paradoxes, which is our final sort of major point of this podcast. Uh, I'm sure, well, I don't know. Most people listening to this have probably seen some kind of sci-fi movie, maybe Terminator. I mean,
Back to the
Inception,
Future.
yeah, Back to the Future, all those types. I mean, just the one Tenet is a really interesting one about time inversion, going back and then going forward again. Um, but there are always these weird paradoxes that arise, and we wanted to cover maybe three of them, three of the most, well, we found most interesting ones. So, how about this? We'll go through each of these paradoxes, but as sort of a setup. Why is it that things start to break down in theory when we go backwards? Is that just because, again, it just goes with the entropy having to go, time having to go forward, and we start thinking about going backwards, it just something breaks?
Yeah, and I think it's also our concept of causation. You know,
Mm,
I think that's the main thing that really that it really gets at is causation dictates our entire lives and our entire understanding of the universe.
okay, so with causation, first up, we have grandfather paradox. So if I was a normal person, I'd say in terms of causation, my grandfather and my grandmother had my mother, and my other grandfather and grandmother had my dad, and then they had me. So that was pretty straightforward. But what if I went back in time and interacted with them? What can you give us a bit more of the paradox itself, and then
Yeah, the paradox, it's a little bit I mean, yes, as
more
many
morbid?
as many physics paradoxes are, they're a little disturbing if you think about them in reality, but imagine just in a hypothetical sense that you went back in time and killed your grandfather. You are only around, when you think about why you exist, like you said, you only exist because your grandfather had you. If you go back to, well, let's say you went back in time to, let's say, just right after your grandfather was born, and then you killed him,
Man,
which is even more
that's
disturbing than killing a baby.
heavy
But
stuff.
yeah,
But it's physics, so it's fine, right?
it's physics. It's just a thought experiment. Um, yeah. So now you have. Would you cease to exist? So the paradox is like, what happens to you now that you have changed the outcome of your existence? And so, um, yeah, I think there's a couple different aspects to this. Most physicists, movies have their own treatise on how they do this, but most physicists would probably argue that this would create the multiverse, which the Avengers talked about having multiple different timelines, that like you have just branched off of the standard timeline and you have created an alternate timeline where your grandfather did not exist, but you do. And It's really difficult for us to fathom that. But if time travel is possible, then there's not really any paradox in there. The timeline where your grandfather did exist still is happening. There's just now an alternate timeline. So that's generally how movies like Avengers and some other movies get around it. Is there's a multiverse.
But would you still exist in both timelines?
Yeah. In the multiverse, assuming time travel is possible, there can be multiple versions of yourself in time.
But but it would seem like even in that second alternate timeline, if you killed your grandfather, what like it would seem like that timeline going forward would just be you not being born, right?
It would seem like that. I mean, it's you know, in terms of physics, I would ask what removes you from that timeline? What physical force takes you out of that timeline, right? Like you've clearly found a wormhole or something to like be able to go back in time. And if the laws of the physics laws of the universe have allowed that, then you're back in that timeline. And if somebody asks you and says, hey, how are you born? It's like, actually, I wasn't born in this timeline. I was born in a different timeline. And I just came and killed my granddad. And they'd probably be like, wow, you're really messed up, dude. So can you go back to your timeline? We don't want you in ours.
But then in that timeline, let's just say there's a third timeline where you don't kill your granddad and you just kind of hang out with him for 50 years. Then eventually you're born again and there's two of you. Would that also be another timeline?
That, well, that would only be two timelines, right? Yeah, you had your original timeline, and then you have a branch where in that branch you either choose to kill him or you choose not to kill him. If you choose not to kill him, yeah, you're on a branch and you exist in that timeline. Yeah, are obviously aging, so you would meet your younger self as your older self.
Well, what about this? So you don't kill your grandfather in the original timeline. So there's a second timeline where you're just hanging out, you get older and older, and then eventually you meet your younger self. But then your younger self grows up, goes back in time, and then he kills you and your grandfather at the time that you came back. What happened? I'm making it more and more ridiculous, but what would happen then?
You're asking some really
Ridiculous questions.
yeah, it's this is why these things are paradoxes, is because we don't currently know how to test these things, and it's a lot of speculation. Yeah, I guess the natural physics example is that the world would exist just how it normally does, and if you were able to travel back in time and create a new timeline, then it's weird, but you're living that timeline just as normal. This is probably a good point to mention this concept of the butterfly effect.
Mm-hmm.
We're going to mention it, I think, in maybe another paradox, but like the butterfly effect says that if a butterfly would have flapped its wings to the left instead of the right when you were born, maybe you would have ended up being the president of the United States, right? That a tiny, insignificant, what you think is insignificant event has far-reaching implications as you sort of map that out from time. And so maybe that's like in that timeline you're living, like you decide not to kill your grandfather, but you stop for ice cream and then they run out of ice cream and your granddad never buys an ice cream cone for your grandmother. And so maybe you are never born. Like you don't know the implications of your actions. So just by you going back in time, there's the butterfly effect would say that there's no way that timeline would still map out where you would exist in it.
Yeah, there would be a new timeline that was created. With the multiverse part, I'm curious if it just seems like the original timeline would cease to exist then. There wouldn't necessarily be two different timelines. There's just a new timeline that occurs.
Well, one of the aspects of quantum mechanics that leads to this multiverse says that every time you make a decision, or maybe even more importantly, every time there is either a quantum fluctuation or some particle is spin up instead of spin down. It creates a different version of that universe.
Yeah.
And so these multiple different universes already exist. Again, we touched on this a little bit in our last podcast, where we talked about an electron taking multiple different pathways, and it'll always take all of them unless you force it to only take one. And so it is mapping out many different multiverses, but still ending up in the same place.
Yes, so grandfather paradox. Let's get off of something as morbid as killing your grandfather and move on to something a lot more happy, like the let's kill Hitler paradox next. So this one's, as you may have guessed already, pretty straightforward. This touches upon butterfly effect too, but I assume what this is it's just, hey, Hitler, worst guy ever. We can now time travel. What if we just went back and then we killed Hitler? Things would be a lot better. So where's the paradox result in this case?
Yeah, I mean, it's probably just in my mind, it's an extension of the grandfather paradox, right? Like if you went back and killed your grandfather, it was almost certainly a great guy, but like what would the future implications of the world be? Like if you fast forward it, how much different would Elon Musk still have come up with the company Tesla? If you go back and kill Hitler, there's a pretty good chance that, tech companies and war efforts and Northrop Grumman and a lot of these companies that make military devices, would they even still be around? And then maybe people don't have jobs, and it drastically changes the economy. So again, it's just meant to highlight the butterfly effect, right? Like how much impact would it have? And so again, I think it's an extension of the grandfather paradox. If you go back and change something major.
Yeah, I mean, okay, so something major. I was going to say you could lump those together and just say, what if Hitler was your grandfather and you went back in time and killed him? Then then it's a paradox inside a paradox.
Ooh, goodness gracious. Yeah.
All right. Anyways, okay. So continuation there, butterfly effect. So finally, we'll end on one that maybe is a bit lesser known, and that's called the Polchinski paradox, which I didn't know about till very recently. Now, correct me if I'm wrong, but this is my understanding of it. Say you're playing pool, right? And you have a billiards ball, and you're about to send the billiards ball towards whatever other billiards ball would help you win the game. And then there's this wormhole that emerges, and you're like, oh, let me send the billiard ball through the wormhole and see what happens. The problem is that the other side of the wormhole comes out right where you would send the billiard ball in. So the problem is once you send it in, it's then going to emerge at the exact same time right where you would have sent it in, and thus it hits itself somehow and then can't move. Is that a half decent summary of this?
Yeah, and it's also very mind-boggling. Yes, you're exactly right. Imagine you're playing pool, and as you hit the cue ball goes into a wormhole, goes backward in time, and then hits itself before it launches. I think that essentially gets to the nature of it, and that is no easy paradox, I think, to resolve. So, the thing I like about this paradox is it does use the physics. It uses physics principles that we understand. We at least can mathematically understand the movement of a billiard ball, and we can understand a wormhole. And so how do you get around the fact that this, how do you get around this paradox? Like what happens then? It goes backwards in time, hits itself. Are there now two billiard balls? Does the billiard ball stop? Does time just completely stop? Does it start going backwards because you've messed it up too much? And there's, I think there was some research done recently It's interesting enough about the butterfly effect, and they did some quantum simulations using qubits, and the finding was that essentially quantum mechanics doesn't really see the butterfly effect have any noticeable difference. They created these states that were reproducible in a quantum computer and reran the simulations, just slightly perturbing the initial state, and the outcome was essentially still the same. We don't know how that scales to the macroscopic level, the world that you and I and everyone else lives in. So I think that part of that research showed that it's possible in something like this Polchinski paradox that if a billiard ball was to go back in time, it would hit the other billiard ball, but in such a way that it still went through the wormhole because there is some deterministic world we went into. They call that, I think, like a timeline protection hypothesis or something, which is really just a theory that physicists put in place to make sure that we don't have to think about this too hard, right? It's just like, don't let it mess it up because it messes up the entire universe.
It's like guardrails, basically. You're on this
Yeah.
high, dangerous road, and you're like, let's put some guardrails up because we're going to fall off.
Right.
Yeah, I guess, I mean, so if we want to sum all this up in terms of these paradoxes in time travel and trying to think about going back in time, I suppose there's probably three different options in terms of what could be true. So one is what we started with the multiverse. So something splits off and a new timeline is enacted. And then the second one is the current timeline is irrevocably changed, basically, right? So whatever you do will the butterfly effect is indeed true, and it does change. I guess there's three then. The third one is, or four then I should say. The third one is that nature itself will go back and is pretty robust. So even if you change something, it's still set towards a determined outcome. And then the fourth one is just you can't go back in time. It's just not possible.
Yeah, I think that's a great summary of it, Josh. Right. Like, and one of the paradoxes that we did not mention was the predestination paradox. So, I don't know why in these paradoxes somebody always has to die, but I'm going to blame Schrodinger on this. Let's say your cat gets run over, right? And in this paradox, you go back in time to find out, I want to see who ran over my cat. And so you're driving around your neighborhood to set up for it. And then you run over your cat and you realize that you were the one who ran over your cat. And so I think that's the scenario you're talking about where the universe is essentially self-correcting. Like anytime you go back, if you go back in time, it's already happened. And so you're in some ways just kind of riding on a timeline that's already happened, right? That's certainly possible. And I think that's a very interesting one to think about because then it takes away this idea that we have control of our lives, right? Where's our choice? Do we not have any sort of choice? And does that mean we don't have choice in our real life? Are we just riding along some timeline?
Yeah, then you get into free will versus predestination. Another simple topic we can save for another time, perhaps. But that itself might be a paradox between the trying to even make a distinction between predestination and free will. I don't know much about it. If I had to guess, I would assume that both exist, if that makes sense. Like on some level, everything has already happened. Again, if you believe in God, God already knows everything that's already happened. But also, you don't know everything that's already happened, and you actually can choose what you want to happen, even if someone already knows what's going to happen. But that gets back to subjective and the relativity of measuring things. All right. Anyways, paradoxes. Those are a lot of fun. I love my mind getting melded or melted, I guess. So we've come to the end of our podcast on time. We won't now start going backwards as might be most fitting for a podcast on time. We just start and work our way to the
and maybe we'll show this podcast in reverse and see if anyone responds to it, then maybe they're going backwards in time.
That's how you test to see if time travel actually works. Yeah, there we go. Well, yes, thanks everybody for listening to this interesting podcast about time. As mentioned before, if you're still listening now and you haven't yet subscribed or smashed that like button, apparently, you can also, if you don't like smashing things, you could just press it lightly. Either way, I'll be okay with it. But please do it. And again, we'll be having a YouTube live follow-up at some point in the indeterminate future or in the past, just depending. We don't know yet. So please stay tuned for that follow-up. But yeah, any other final comments or thoughts you wanted to add here, Lee?
No, I think this was one of our most exciting ones. I think you're right. It's really fun to end with paradoxes. So
we should make that a tradition.
Yeah, end with a paradox. We'll try to make that a tradition since those are so fun to think of.
Sounds good. All right, guys. Well, again, thanks for listening. Enjoy the rest of your day. And yeah, if you have any questions, feel free to, again, always comment on the video or email through my podcast, which again is whywoulidipodcast@gmail.com. All right. Thanks, everybody.
Thank you much.